All right, let's do a little heat engine problem here. You have 50,000 joules of thermal energy flowing into a heat engine. If the heat engine converts 5,000 joules of the heat into work, A, how much heat flows into the low temperature reservoir? And draw a heat engine diagram. And what is the efficiency of the heat engine? Did I spell reservoir right? Does that look right? I don't know. Somebody check that for me. Anyway, so let's do the given. And I like to draw a picture in what's given. So I'm even going to do part B as part of what's given. We have some kind of high temperature. And heat flows from high to, then we have low temperature. Oops. Now, remember, this is a schematic, a diagram that has nothing to do with the actual, what a heat engine actually looks like, okay? It's just representing, like the high temperature in like an old-fashioned steam engine, it could be the boiler. You know, you're throwing coal into this thing and it's burning, it's getting really, really hot, and that heat is transferred in the boiler. And then you've got, you know, some kind of piston system here. It's usually pistons. And this represents the heat that flows into the heat engine. And then heat flows out of the heat engine into the low temperature reservoir, but some of it, the heat is actually converted into work. Now, I call this is heat flowing. Heat flows from high to low temperature. Always does. That's the second law of thermodynamics. So heat's going to flow like this. Some of it gets turned into work. So this is the heat that flows out of the high temperature, measured in joules. This is the work done, measured in joules. Now this is the heat that flows into the low temperature reservoir. And what we say is that the heat, to conserve energy, well, actually, let's do find. We want to know how much heat flows into the low temperature reservoir. And we want to draw a heat engine diagram. Did that in what's given. That's the answer for part B. And then we want to find, so for A, and then for part C, we want to know what is the efficiency. And I'll just write that as E, for little e for efficiency. So let's solve it. Well, the first law of thermodynamics says that the energy that enters your heat engine has to be equal to the energy that leaves. A heat engine cannot create or destroy energy. It only can, you know, do different things with it. So the energy in equals the energy that flows out. Okay? So we want to know how much heat is has to be flowing into the low temperature reservoir. So we solve for it. Okay, so the heat flowing into the low temperature reservoir, well, we've got 50,000, I didn't write it up here. QH equals 50,000 joules. Q low, or work done, is 5,000 joules. So this is going to be 50,000 joules minus the work done. So this is really easy to do. I mean, the arithmetic is trivial. The concepts are important. Okay? So if you're only getting 5,000 joules out of this thing, where's that other 45,000 joules got to go? Out the exhaust pipe, into the environment, wasting high quality energy and turning it into low quality energy. So So this is our answer for part A. Now for part C. Well, the efficiency is equal to what you get out of it that you want. You want to turn as much of the energy as possible into useful work, divided by what you put in. So it's the work you get out of it divided by the heat that you put into it. Notice they're both in joules. Well, 5,000 divided by 50,000 is 0.10. And if you want to express that as a percentage, the efficiency is 10%. Okay? So it's only turning 10% of the heat into useful work. The rest of it's wasted. And that isn't all that untypical of a heat engine. Let's zoom out. Okay. And you'll have a problem like that on the test. So if you understand the concepts, it's really a pretty easy problem. Does that make sense to everybody? Any questions? That is all.